welcome to a journey through time. A journey that takes us back 4.5 billion years to a time before Earth existed, before the sun burned bright in the sky, before any planets circled in their orbits. This is the story of how our solar system came to be, a story written in the language of gravity, chemistry, and time itself. Imagine, if you will, a vast cloud of gas and dust drifting through the darkness of space. This cloud, known as the solar nebula, stretched across billions of miles of empty void. It was cold, unimaginably cold, and mostly made of hydrogen, the simplest and most abundant element in the universe. Mixed within this hydrogen were traces of helium and even smaller amounts of heavier elements: carbon, oxygen, iron, silicon, all the building blocks of worlds yet to come. This nebula was not alone in the universe. It was part of a larger molecular cloud, one of many scattered throughout our galaxy. For millions of years, this cloud simply existed, drifting slowly through space, subject to the subtle gravitational pulls of distant stars. The particles within moved almost imperceptibly, occasionally colliding, sometimes sticking together, but mostly just floating in the vast emptiness. But then, something changed. Perhaps a nearby star reached the end of its life and exploded in a brilliant supernova, sending shockwaves rippling through space. Or perhaps the gravitational influence of a passing star disturbed the delicate equilibrium of the cloud. Whatever the cause, a disturbance began. A ripple moved through the nebula, compressing the gas and dust in certain regions. And where compression occurs, gravity grows stronger. The denser regions of the cloud began to pull in more material from their surroundings. Slowly at first, then faster. Gravity is patient but relentless, and over thousands of years, the cloud began to collapse inward toward its center. As it collapsed, something remarkable happened. The cloud began to spin. This rotation was not random. It followed the fundamental laws of physics, the same laws that cause a figure skater to spin faster when they pull their arms inward. As the solar nebula contracted, it spun faster and faster. The once spherical cloud began to flatten, spreading out into a disk shape, a cosmic pancake of gas and dust, with a dense, hot center and material swirling in orbits around it. At the heart of this collapsing cloud, where material was densest and falling inward most rapidly, temperatures began to rise. The compression of gas releases energy, transforms gravitational potential energy into heat. The center grew hotter and hotter still, thousands of degrees, then tens of thousands. The hydrogen atoms collided with increasing violence, their electrons stripped away by the intense heat, creating a glowing ball of plasma. This proto-sun, as we call it, was not yet a true star. It was still gathering mass from the surrounding disk, still growing, still heating up. But already it dominated the young solar system, containing most of the mass of the entire nebula. Its gravitational pull controlled everything around it, determining the future of all the material still swirling in the disk. Meanwhile, in the disk itself, a different process was unfolding. The tiny particles of dust, grains smaller than those in smoke, were beginning to stick together. At first, this was a gentle process. Dust grains have irregular surfaces, and when they collided at low speeds, electrostatic forces and molecular attractions caused them to cling to one another. Grain by grain, particle by particle, slightly larger clumps formed. These clumps, now perhaps the size of pebbles, had a greater gravitational pull than individual dust grains. They attracted more material, growing larger still. From pebbles came boulders. From boulders came objects the size of mountains, then larger still. This process, called accretion, accelerated as objects grew bigger. Larger objects had stronger gravity, which helped them sweep up more material from their orbital paths. Over hundreds of thousands of years, these growing bodies, called planetesimals, began to dominate different regions of the disk. Some were a few miles across. Others grew to hundreds of miles in diameter. They collided with one another in slow-motion cosmic demolition derbies, sometimes shattering, sometimes merging into even larger objects. The early solar system was a chaotic place, a shooting gallery of colliding rock and ice. But gradually, order began to emerge from the chaos. Certain planetesimals, through a combination of fortunate location and random chance, grew larger than their neighbors. These growing protoplanets cleared their orbital zones, absorbing or ejecting smaller objects through gravitational interactions. The position of these forming planets in the disk was crucial to their ultimate nature. Closer to the young sun, temperatures were much higher. In these inner regions, only materials with high melting points could remain solid. Rock-forming minerals, silicates, metals like iron and nickel, these were the building blocks of the inner planets. Mercury, the closest to the sun, formed in a region of intense heat. The lighter materials were blown away by the solar wind or evaporated by the heat, leaving behind a world rich in heavy metals. Even today, Mercury has a disproportionately large iron core for its size. A remnant of its formation will sit in the hottest part of the disk. Venus formed next, in a region still hot, but slightly cooler than Mercury's birthplace. Here, more minerals could condense and accumulate. The planet grew larger, with a thick rocky mantle surrounding a metallic core. As it grew, its gravity began to capture some of the gases from the surrounding nebula, the beginnings of an atmosphere. Earth formed in what we might call the temperate zone of the young solar system. Here, temperatures allowed a diverse array of minerals to condense. The growing Earth accumulated layer upon layer of rock and metal. Its interior heated from the energy of countless impacts and from the decay of radioactive elements trapped within. This heat caused the planet to partially melt, allowing heavy elements like iron to sink toward the center, forming a core, while lighter minerals rose to create a mantle. But Earth's formation was not complete yet. Sometime during its early history, perhaps 50 million years after the solar system began to form, Earth experienced a catastrophic collision. Another planet-sized body, about the size of Mars, struck Earth in a glancing blow. The impact was so violent that it melted both bodies, ejecting vast amounts of material into orbit around Earth. This orbiting debris quickly coalesced under its own gravity, forming our Moon. The Moon's composition reflects this violent birth. It has a much smaller iron core than Earth, because the collision primarily ejected material from the mantles of both bodies, not their dense cores. Mars formed in the outer reaches of the terrestrial planet zone. Here, the density of material in the disk was lower, and Mars never grew as large as Earth. Some scientists believe that the gravitational influence of Jupiter, forming in the outer solar system, disrupted the disk in Mars's region, preventing the red planet from accumulating more mass. Mars formed quickly, perhaps in just a few million years, and its smaller size meant it cooled more rapidly than Earth. Beyond Mars, in the colder outer solar system, a different kind of planet was forming. Here, temperatures were low enough for water ice to condense as a solid. This dramatically increased the amount of solid material available for planet building. Water is abundant in the universe, and having it available as ice meant much more mass was available to form planets. Jupiter formed in this ice-rich region. A large core of rock and ice, perhaps 10 times the mass of Earth, formed first. But this core grew large enough to have a significant gravitational pull on the surrounding gas. The core began to capture hydrogen and helium directly from the nebula, accumulating gas at an accelerating rate. In a relatively short time, perhaps just a few million years, Jupiter ballooned to become the giant we see today. A planet made mostly of gas, with a small rocky core buried deep within. Jupiter's formation had profound effects on the rest of the solar system. Its immense gravitational pull stirred up the asteroid belt region between it and Mars, preventing a planet from forming there. The asteroids we see today are the leftover building blocks, planetesimals that never merged into a larger body because of Jupiter's disruptive influence. Saturn formed next, following a similar pattern to Jupiter. A core of rock and ice captured gas from the nebula, growing into another gas giant. Saturn is somewhat smaller than Jupiter, perhaps because it formed later when less gas remained available, or because it formed farther from the Sun where the disk was less dense. Uranus and Neptune formed in the outer reaches of the disk, in the cold, sparse regions far from the young Sun. Here, planet formation was slower. There was less material to work with, and particles moved more slowly in their orbits, taking longer to collide and merge. These ice giants, as we call them, are different in composition from Jupiter and Saturn. They have smaller atmospheres of hydrogen and helium, and larger proportions of ices, water, methane, and ammonia in solid and liquid forms beneath their cloud layers. Some scientists believe Uranus and Neptune may have formed closer to the Sun, perhaps between where Jupiter and Saturn are now, and later migrated outward to their current positions. Gravitational interactions between the giant planets and the remaining planetesimals in the disk could have caused such migrations, reshaping the architecture of the outer solar system. As these planets grew and evolved, the Sun at the center of the system continued its own transformation. The proto-Sun's core grew ever hotter as more material fell into it. The pressure at the center became immense, millions of times the atmospheric pressure on Earth today. The temperature climbed to millions of degrees, and then, somewhere between 10 and 50 million years after the solar nebula began to collapse, the Sun's core reached a critical threshold. The temperature and pressure became sufficient for nuclear fusion to begin. Hydrogen atoms, stripped of their electrons in the plasma, began to fuse together, forming helium and releasing tremendous amounts of energy in the process. The Sun ignited. The nuclear furnace at its core began to burn, and it has burned steadily ever since, for 4.5 billion years. With the Sun's ignition came a powerful solar wind, a stream of charged particles flowing outward from the Sun in all directions. This solar wind began to clear the remaining gas from the inner solar system, blowing the lighter elements out toward the outer reaches or beyond. The era of planet formation was ending. The gas needed to create more giant planets was being swept away. For millions of years after the planets formed, the solar system remained a violent, chaotic place. Leftover planetesimals continued to collide with the planets in what is called the Late Heavy Bombardment. The Moon's heavily cratered surface preserves evidence of this era, a time when impacts were frequent and devastating. Earth, too, was bombarded, though plate tectonics and erosion have erased most evidence from Earth's surface. Some of these impacts may have delivered water to Earth. Comets from the outer solar system, rich in ice, crashing into the young planet. Other impacts brought organic molecules, the chemical building blocks of life. The bombardment was destructive but also creative, reshaping planetary surfaces and potentially seeding the inner planets with ingredients for life. Gradually, over hundreds of millions of years, the bombardment slowed. Most of the loose debris had been swept up by the planets or ejected from the solar system entirely. The planets settled into more stable orbits. The young solar system began to resemble the one we know today. The Sun, now burning steadily, created zones of temperature in the solar system that would remain relatively constant for billions of years. Mercury, closest to the Sun, became a scorched world of temperature extremes. Venus, with its thick carbon dioxide atmosphere, developed a runaway greenhouse effect that made it the hottest planet in the solar system. Earth, at just the right distance from the Sun, maintained temperatures that allowed water to exist as a liquid on its surface, a key requirement for the development of life. Mars, smaller and farther from the Sun, grew cold. Its thin atmosphere could not retain heat effectively. Water that may once have flowed on its surface froze or escaped into space. The red planet became a frozen desert. The gas giants settled into their orbits, their immense gravitational fields creating complex systems of moons. Jupiter captured dozens of moons, some captured asteroids, others formed from disks of material around Jupiter itself, similar to how planets formed around the Sun. Europa, Ganymede, Callisto, and Io became worlds in their own right, each with unique characteristics shaped by Jupiter's powerful gravity. Saturn's magnificent rings formed, either from a moon torn apart by tidal forces or from material left over from Saturn's formation that never coalesced into a moon. The rings spread out in a thin, flat disk, made mostly of water ice particles ranging in size from dust grains to house-sized chunks. Uranus and Neptune, in the cold outer darkness, developed their own systems of moons and rings. Triton, Neptune's largest moon, likely a captured object from the Kuiper Belt, orbits backward compared to Neptune's rotation, evidence of a violent capture event in the distant past. Beyond Neptune, in the frigid outer reaches of the solar system, billions of small icy bodies orbit in the Kuiper Belt. These are the remnants of planet formation, objects that never accreted into larger bodies because the disk was too sparse and temperatures too cold for rapid growth. Among these Kuiper Belt objects is Pluto, now classified as a dwarf planet, along with hundreds of other similar worlds. Even farther out, in the most distant reaches of the Sun's gravitational influence, lies the Oort cloud, a vast spherical shell of icy objects surrounding the entire solar system. These objects are the most pristine remnants of the solar nebula, largely unchanged since the solar system's formation. Occasionally, gravitational perturbations from passing stars send one of these objects falling inward toward the Sun, where it becomes visible as a comet, a visitor from the deep freeze of the outer solar system. And so our solar system took shape. From a cold cloud of gas and dust, gravity sculpted a star and a family of planets. From chaos came order. From simplicity came complexity. The process took millions of years, but in cosmic terms it was remarkably quick. Today, 4.5 billion years later, the solar system continues to evolve. The Sun slowly brightens as it ages. The planets continue their endless orbits. Moons slowly spiral outward or inward due to tidal forces. Asteroids occasionally collide, creating new fragments. Comets venture in from the outer darkness, only to evaporate in the Sun's heat. But the basic structure established in those first few tens of millions of years remains. 8 major planets orbit the Sun in roughly circular paths, all in approximately the same plane, a remnant of the flat disk from which they formed. Rocky worlds orbit close to the Sun. Giant worlds orbit farther out. Asteroids and comets preserve evidence of the building blocks that formed the planets. And on one of those rocky worlds, the third from the Sun, life emerged. Single-celled organisms appeared in ancient oceans, evolved, diversified, and ultimately gave rise to beings capable of looking up at the night sky and wondering about their origins. We are, in a very real sense, children of the solar system, made from atoms forged in the hearts of ancient stars, assembled on a planet that coalesced from cosmic dust, evolved under the steady light of our sun. The formation of the solar system was not unique. Around other stars, other planetary systems have formed and continue to form today. Telescopes have revealed thousands of exoplanets orbiting distant suns, each with their own formation story. Some are like our solar system. Others are wonderfully strange. Hot Jupiters orbiting closer to their stars than Mercury orbits our Sun. Super-Earths with no equivalent in our system. Planets orbiting binary stars, or even free-floating through interstellar space. But our solar system is special to us. It is our home. From the Sun's fusion fires to the frozen comets of the Oort cloud. From Mercury's cratered face to Neptune's deep blue clouds. It is a system we are only beginning to truly understand. Spacecraft have visited every major planet, and new missions continue to explore the asteroids, moons, and dwarf planets that complete our cosmic family. The story of the solar system's formation is still being written, not with gas and dust, but with observations and calculations, spacecraft data and computer simulations. Each new discovery adds another detail to our understanding, another piece of the puzzle. And as you drift off to sleep tonight, consider this. You are lying on a planet that formed from cosmic dust, orbiting a star born from a collapsing nebula, in a solar system that emerged from chaos through the patient work of gravity and time. You are part of this story, made from the same materials, subject to the same physical laws, connected to the cosmos in the most fundamental way. Good night and dream of stars.